So good morning, I'm Flora Poon from St. Stephen's Girls' College. To begin with, let me introduce to you what this project, How to Keep Water Cold 2, is about. So given a cubic container of sides of length A containing a fixed volume of water V, we can rotate the cube about a vertex O to change the contact area between the water and the wall of the cube. We would like to find out when is the minimum contact area and when does this happen. I've divided the problem into three parts, finding the smallest contact area when the cube is rotated along one side, when the cube is rotated about vertex O on the group floor while keeping plane ABOC vertical, and when the cube is rotated freely about vertex O. I've studied the rotation of a cuboid along one side as well, which is a more general case and is helpful for the first part of the project. So when the cube is rotated along one side, the shapes of water throughout the rotation process are rather simple. I got the following results by simple calculation and comparisons. Now we come to the second part when the cube is rotated about vertex O while keeping plane ABOC vertical. In part 2a, the volume of water is smaller than a cube over 6. We let theta be the angle BOD. As theta decreases, there can be 4 different shapes of water and can be treated as subparts. The first one is when the water covers the entire base of the cube. Firstly, we would prove that A, F, and C are collinear when AFCEHI is laid flat. We connect A to C and AC crosses the other diagonal at B, and we let the length of FG be H. By comparing the slopes of different line segments, we get CD equals to 2H. Thus AF and C are collinear. Then we can treat AFCEHI as a trapezium, and by symmetry we get the other one on the other side and also the square base. Then we can get the contact area by simple calculation. As theta decreases, the water now has a pentagonal top face. After expressing the contact area in terms of A, x, which is OS, and theta, we find the expression to be very complicated. We will solve it using numerical method instead. The details of it will be explained later. As theta further decreases, the water becomes pyramid in shape. After writing out the contact area in terms of K, which is OC, and V, we use differentiation to find the minimum value. When theta becomes even smaller, the water becomes a frustum with 2 triangular bases. We use the Lagrange multipliers to find the extreme values of the complicated expressions for contact areas. Afterwards, we compare the size of extreme values with boundary values and get the minimum one. After getting the smallest contact areas in each of the 4 subparts, we can compare them for the smallest. In fact, throughout the whole project, we use the following 3 methods for comparisons: factorization, Cardano's formula, and numerical method. In part 2a3, I factorized the difference of 2 expressions into a perfect square for comparison, in which it is always larger than 0. In that way, we would know that one of them is always larger, regardless of the size of the variables. We've used the Cardano's formula in comparing the contact areas in part 2a5. We equate the 2 expressions and we get a cubic equation. We can reduce it into a form that the Cardano's formula can be applied easily by substituting x equals to 1 over root a. We found the 2 imaginary roots and we eliminated the imaginary parts by converting them into polar forms. By using the solver in Microsoft Excel, we can compare complicated expressions using the numerical method. We set up constraints for some variables and solve for the extreme values for the finite number of cases. There might be uncertainty on cases we have not tested, but we can always put the case into the solver and solve it. After comparing for the smallest contact area among the 4 cases, we got the following results. For different V's, there could be 2 different smallest contact areas. For part 2b, the volume of water is smaller than a cube over 2 and larger than a cube over 6. As theta decreases, the shapes of water are the same as that in part 2a, except for the third stage when the water is a frustum with a triangular and pentagonal base. Indeed, the contact area of this case is difficult to be expressed with no more than 3 variables. However, adding 2 smaller pyramids, like these 2, can transfer it into a frustum with 2 triangular bases. Thus, the expression for contact area becomes similar to that in part 2a4, and is simple enough for us to use the numerical method for further comparison. After comparison between all four subparts in part 2b, we know that 2v over a plus 2 times root 2va is the smallest contact area when theta equals to 0 degree. For part 2c and d, the volume of water is larger than a cubed over 2. Note that in this case, the wet area is 6a squared minus the dry area, which has already been studied in part 2a and b. By subtracting the largest possible dry area from 6a squared, we know that for both cases, the smallest contact area is a squared plus 4v over a when theta equals to 0 degree. We will now study part 3, when the cube is rotated freely about a vertex O. First, we will define OD and OE be two lines on the ground which are perpendicular to each other. We can simplify the free rotation into two rotations in different dimensions. First one is to decrease the size of angle BOD, which is theta, while keeping the plane ABOC vertical to the ground. Second one is to decrease the size of the angle which the plane ABOC makes with the horizontal ground, which is lambda. In part 3a, when the volume of water is less than a cubed over 6, the shapes are similar to that in part 2a, except that they are no longer symmetrical on the side. The contact areas in part 3 can be written into similar expressions in part 2, and by crossing out the common terms, the minimum contact area can be found by simple comparisons or differentiation, or we use the Lagrange multipliers to solve the expression with three variables. In part 3a3, the water is pyramid in shape. We define the length of CO be k. We let gamma be the angle which AO makes with the ground on plane DFOE. We get this one, in the new contact areas expression, which is similar to that in part 2a3. Whether the new contact area is smaller than the original one depends on the factor half root tangent gamma plus root cotangent gamma. By differentiation, we find the smallest wet contact area, which is the same as that in part 2a3 when gamma equals to 45 degrees. Now I would like to make an amendment on page 60 of my report by switching the method used to Lagrange multiplier in part 3a4. I first set up the two equations related to the contact area S and the volume of water V respectively. Then I solved the three equations involving partial derivatives for x, y, and gamma. CE equals to BO, which is the same as part 1a, and gamma equals to 45 degrees, which is the same as part 2a, are the possible criteria for extreme values to occur. By further comparisons, the smallest contact area is the same as that in part 2a. In fact, we find the minimum contact area occur when lambda equals to 90 degrees for all subparts in part 3a. This is true for part 3b, c, and d as well for similar reasons. Finally, the results for two special cases, v equals to a cubed over 2 and v equals to a cubed, are 3a squared and 6a squared for all angle theta. To sum up my findings in my report, here is the result table showing the smallest contact area and corresponding angles for different volumes of water. So this is the end of my presentation. Thank you.